Outcome?
Yeah,
Remote, right? Homework 6. You today. But I said I'm flexible, so it can be made all the way in next working Tuesday. So it's all the way up. But finish it off, that's my recommendation. So this one, let's make it. You have, because it's right after holidays, so that shouldn't be a reason to postpone. That clear?
the 21st.
Oh, sorry, not 7. That's the confusion. That's when everyone is spelling. Anyone? Better first. And midterm 2, I don't have it here. I think that is in April. April 20th. So, yeah. Okay. Maz gives that he said he's not feeling well, so he wants to get. Right. 6 of us, okay. Okay. So we were doing relativistic kinematics, and we want to soon introduce Newton's laws in this context. And we should be able to talk about electric and magnetic field, how a charge behaves in an electric and magnetic field in the relativistic sense. So let's quickly, let's begin with kinematics, relativistic kinematics, and quick review. Maybe position. So this is 4th position. This X alpha, PT, and position R, space position, and time. We defined for velocity as C times the derivative with respect to a proper distance, and this leads us to the idea that this is C times gamma and V times gamma. Remember, we are using the idea that ds is equal to C times dt, and times gamma as it is. Right, yeah. In this, the basic aim is that if we can identify such a 4 vector, X alpha. X alpha is invariant, we can go to any frame and that will remain the same. Same thing with U alpha. U alpha, that remains invariant. In fact, this comes out to be equal to C squared itself. In fact, minus C squared, right, comes out minus C squared. So that's the convenience of this four velocity, four vectors. And we also define for momentum. Basically, P alpha is mass times the force velocity, which gives mv. That's all good, but now we identify or we define in a sense. This is not straightforward going from here, but this is a postulate if you want that this is a momentum and energy. So this is an input, like this is a physical input. And it's a postulate. It's not really an equality in the sense you cannot derive this relation itself. It's a definition. So that's where we were, and then we started talking about for acceleration. Let's quickly do that acceleration. We began on this. We will define this as C times derivative of for velocity with respect to proper distance and for diameter. Otherwise, the recording will not happen. Yeah, good that you guys observe all these things. Okay. Okay, so for acceleration is the derivative with a proper time derivative of u alpha, so that's d by dt of u alpha is c times gamma velocity gamma. We can do one more thing, we can actually take the derivative, right? So this is let me keep gamma outside, c times derivative of gamma with respect to time. Now I can take derivative with velocity or gamma. So this is either I take the derivative with respect to the Lorentz factor, or when I take the derivative with v, that's defined as the acceleration. That's okay. And notice acceleration still is the usual the Newtonian acceleration, right? Derivative of velocity or derivative of the Newtonian velocity with respect to time. The velocity really has not changed in this configuration, but the force acceleration is having this combination in this form. So when we talk about what is invariant, This is not going to stay invariant because this is only a component. It's not even a component, it's something inside a component. Right, so in that sense, it's not expected that acceleration is going to stay the same. When you go from one frame to the other, it's not a Lorentz invariant quantity. So what is Lorentz invariant quantity? So let's process this a little bit. It's convenient to take the derivative of gamma. So let's do that. So gamma, remember, is equal to 1 over 1 minus v dotted with v over c squared. If I'm taking the time derivative of gamma, the only place where the time derivative hits is the velocity itself. So it is 1 by 2 times 1 over 1 minus v dotted with v over c squared. Well, so raised to minus 1 by 2, right? Because it's power of 1 by 2 in the numerator, minus 1 by 2, and then minus 1 by 2, minus 1, and 3 by 2, minus 3 by 2, bring it down in the denominator, minus 3 by 2, and then the derivative of the argument, that is 1, and that is minus 2 times v dotted with dv by dt, and that is c squared. Is that clear for you? Just the standard derivative. I have to hit this velocity, which is the acceleration, to reach, and then I have to do the chain rule. So minus 2 and 1 over 2 in the denominator cancels out, and this is nothing but, this is gamma cube, right? This whole thing. So this is gamma cube, and you have v dotted with acceleration over c squared. That's it. A relation you have for the derivative of gamma with respect to time. Just standard algebra. Is that clear? Any questions? Okay, so you can put that in here, and we get acceleration to be equal to gamma is still there. So this is equal to c times, that is a gamma cube, and v dotted with a over c squared. So we can actually cancel out 1 over c if we want to. And this is v times v dotted with acceleration over c squared again, plus gamma cube also. Gamma cube plus acceleration times gamma. That is one thing one can do immediately, and that is let's consider two situations. What happens if v was parallel to acceleration? That's a special scenario. If you start from rest and you, let's say there is an electric field, and if you start from rest, only if you start from rest, then the velocity it will pick up will be in the direction of the electric field itself, right? So in that case, velocity and acceleration are expected to be the same. But if in relativity it doesn't happen, that maybe I should clarify. If there is an electric field in this direction, and you throw a charge in this direction, right? Classically, what happens is that there is an acceleration in the direction or in the vertically downward direction, no acceleration in the horizontal direction. So the velocity v remains the same in the horizontal direction, and in the vertical direction, it accelerates. Right. But that's not what happens in relativity. There's an acceleration in this direction. But in relativity, the velocity here will not remain the same. Accelerate in that direction also. Okay, so it is it's a proper acceleration that remains the same. And that will be part of the homework to see how the velocity changes in the horizontal direction. That will be a problem in your homework. What I will do is a simpler problem when velocity is equal to 0, starts from rest. So in that case, it keeps accelerating in the downward direction.
But it also accelerates in.
No, if you start from rest, then it's not going to accelerate in that direction. So then it will
In the direction of.
in the direction of the electric field. But if you give it a small velocity in that direction, then the rest frame, remember always that Wigner rotation comes into picture, so that that contribution is always in there. So non-trivial in that sense that, oh, where did that acceleration come from? But that will be an acceleration there. Remember, acceleration is not a covariant quantity, or acceleration in here is not an invariant concept. Right? So when we say that is acceleration in the Newtonian physics sense, we should be careful. So we have to go to the rest frame and then figure out what it is. Okay. So with that idea, let's think of a situation where velocity and acceleration is parallel. And if you start from rest, electric field is a situation. Then A alpha is equal to parallel. If it is parallel, V and A is cosine of 0. Cosine of 0 is 1. Then you have gamma times C cancels out. So we have beta there. So there is a beta gamma cube. And then there is acceleration. They're all in the same direction. So let's say that's your acceleration A. And here we have beta square. Then we have acceleration and gamma cube. And plus acceleration again. And there is gamma. Let me wait for a minute. Okay, let me not go in here. Let me introduce one more concept, because we are talking about the invariant of velocity, right? Let me hold on. So I was moving ahead a little faster. So let's have the quantity. Remember, U alpha is equal to minus C squared. We talked about that here. Right, that is minus C squared. Take the derivative here immediately. You get U alpha times A alpha is equal to 0. If you have a quantity like this, where you have one 4 vector and another 4 vector being equal to 0, it's called orthogonality as far as 4 vectors are concerned. But that also means that if this is a time-like vector, this will be a space-like vector. Right? That was one of your homework problem. This implies that A alpha is space-like. You can go to the rest frame in which there is only U0 in here. U0 times A0 is equal to 0. So A0 must be equal to 0. So the time component of A0. So A alpha is space. It's like, if that is the case, there exists a frame. So there exists a frame. So this is, there exists a frame, right? So choice in which this is purely 0. And like you can think of it as a rest frame. So everything goes away here except this acceleration, right? You're in the rest frame of this particle. So everything goes away. Notice V will go away. all the v's goes away, gamma becomes 1, and you just have acceleration. And let's call that, since it's a special frame, this is equal to A. Is that clear what I did? So maybe you can say it is a rest part of it. You're saying that you're actually accelerating, but in your rest frame, you still have an acceleration. In your rest frame to have an acceleration, is that okay? In your rest frame, your velocity is equal to 0. Does that mean the acceleration is 0? If your velocity is 0, what is the acceleration?
Should also.
Gravitational. Gravity.
Yeah, tell me again.
Gravitational acceleration.
Remember, what I'm trying to say is that v is 0 at time t equal to, at some time, velocity is 0. What is acceleration in the sense of derivative of velocity with time? If this is 0, what can you say about this quantity at t? Okay, only at t. Right? It's not always 0. It's not as a function, it is not equal to 0. What can you say about the derivative of the velocity? It doesn't have to be 0. The classic example is when you throw a stone up in the air, right at the top of the curve, velocity is 0, but acceleration is not 0. So this at t, okay, so this is done. If I say is equal to 0, it becomes a function of, if it is 0 all the time, then of course acceleration is 0. But just at one point, velocity being 0 doesn't mean that acceleration is 0. So it's in that sense, when you say that you're on the rest frame of the particle, at that instant, so only on that frame, it is 0. If it's accelerating and you want to be at rest, you want to keep changing your frame. Is that clear what I'm trying to say? If you're an accelerating body, if you're in the rest frame of the object, your Lorentz frame has to keep on changing. It's not the same Lorentz frame you're in. Your velocity is changing if you want to keep changing. So you have to jump from one frame to the other as the particle is accelerating. Like you start from rest, it's at 0 frame. The moment you gain a little velocity, you jump onto that frame. Oh, now I'm at rest. But it's accelerating, so you have to keep jumping from one Lorentz frame to the next Lorentz frame.
So to be remaining in the rest frame.
To remain in the rest frame, exactly. So in that sense, its acceleration need not be 0 when you're rest frame, when you're in the rest frame. So that concept of keeping on jumping from one frame to the other, that plays an important role in the whole of, we may not use it so much, but in relativity and general relativity more, you need to have that idea that you're keeping on jumping from one frame to the other. So there exists a frame anyway, where the acceleration is purely space-like. And in that particular frame, what is A alpha, A alpha? In that particular frame, A alpha is easy to calculate, minus 0 square plus A naught dotted with A naught. That's the magnitude of the proper acceleration. So this now, so magnitude of this square, so let's say A alpha or A naught is called the proper acceleration. That is, I measure this or I define this in a very special phrase. But once I have defined this, this is a Lorentz invariant concept because it is given in terms of square root of this quantity. This is Lorentz invariant. I can go to any frame, calculate this, which will be a big, this is a tedious thing to calculate, but if you were to calculate the square of this quantity minus the square of this quantity, it will come out exactly this. This is not going to change. Is that clear? Because it is a Lorentz invariant concept, I can go to any frame and do that. that clear what I mean?
Say that again.
Okay. I take A alpha here. Calculate A alpha in this frame. Right, where it is not the rest frame, it is not rest frame until here, right? Which will be a tedious way of calculating it. Square this quantity. Take the negative sign of that. Square this quantity. And combine them together. What will I get? I will still get this. Because it's Lorentz invariant. Right? It doesn't matter which frame I calculate. Correct? So this quantity remains the same in every frame. So I define it as proper acceleration because it's a Lorentz invariant concept. If this quantity is compared between different frames, let's say you do an experiment, I do an experiment, we will match. The magnitude of that, notice this is not equal to this. Right? This is in the rest frame. This is not an equal sign in the strict sense. I changed my frame in going from here to there. So this is not equal to this quantity. Right? It is the squared quantity that is the same. So this now you can talk. So even though we cannot talk about acceleration as a concept, as a Lorentz invariant concept in relativity, proper acceleration is a Lorentz invariant concept. So you can talk about a particle going with a proper acceleration of so much, which means that will keep changing as you go from one frame to the other, but this concept will remain the same, the magnitude without that. Clear? So it's good to ask, how does a proper acceleration change from one frame to the other? So let's talk about velocity being parallel to acceleration, as I said earlier. So this is equal to so velocity being parallel to acceleration, I said implies A alpha is equal to, I have to set this is equal to it is the same, correct? So this is equal to gamma times C times gamma cube beta, and one of the C goes away, times acceleration, comma, V is beta squared, acceleration, gamma cube, plus acceleration times gamma. Is that clear? But I'm interested in the proper acceleration squared is equal to the A alpha. I can, for calculating the square of a quantity, the Minkowski magnitude, I multiply the square this with a negative sign. So this is gamma 4. So this is gamma 8. Gamma 8 beta square acceleration square. Minus of that. And come back in here. This is positive. That's beta square A gamma raised to 4 plus A gamma square whole square. Put this together. This is minus gamma 8 beta square A raised A square plus beta raised to 4 gamma raised to 8 A square, and put this plus A square gamma 4, and a combination of this, right? 2 times A square, 2 times A square beta square, and gamma 6 Hopefully, I got all this right. Let's see. That is an a square surely common in everything. And what's the minimum power I have? Gamma raised to 4, I suppose. Right. A square and gamma raised to 4, that's common. That's 1. And this one, a square gamma raised to 4 gone, so that's minus beta square gamma raised to 4. A square gamma square, no, gamma 4. So this is plus beta raised to 4 gamma raised to 4. And so that's done. And plus 2 times gamma 4 gone beta square gamma square. Correct? Think so? Correct me. This is gamma 4 common, maybe that simplifies a square gamma raised to 4 1 minus beta square gamma square, no, gamma raised to 4, so that's 1 minus beta square. This is gamma square in the inverse sense. So gamma this times this is gamma square. So that's equal to a square gamma raised to 4 1 minus beta square gamma square plus 2 beta square gamma square. And that's 1 minus beta square gamma square. Right? So a square gamma raised to 4 1 plus beta square gamma square. What is 1 plus beta square gamma square? Probably again simplifies. Gamma square is 1 plus beta square over 1 minus beta square. So that's 1 over 1 minus beta square. So that's gamma square. Right. So I think that's gamma square. So that's a square gamma raised to 6. Remember, a is the acceleration square, right? This a is the acceleration as measured in a frame, any frame, not necessarily in a moving frame. This gives you a contraction formula if you want, like a square is equal to vector a dotted with vector a times gamma 6. We talk about length contraction, time dilation, and what happens to the acceleration in a moving frame. So acceleration in a moving frame is equal to acceleration in its rest frame divided by gamma cube. Right. So in a sense, how does the acceleration change? It contracts in a sense, but not as gamma, but it's as a Lorentz factor cube comes into the picture. So that's one simple connection. If this is different, if velocity is perpendicular to the acceleration, this is only if velocity is parallel to acceleration. If velocity is perpendicular to acceleration, your results change, which is slightly easier. These two go to 0, right? So we can immediately say that acceleration A alpha is equal to 0 in that case. Like this is 0, that's 0, and you immediately have a gamma square. And then you have an easier idea that a naught square is equal to a alpha is equal to a divided with A times gamma raised to 4. So magnitude of A is equal to the magnitude of A in the rest frame over gamma squared. So notice the contraction that we talk about in the acceleration, it shouldn't be used. The word contraction is not correct, right? Because contraction has to do with the length. If you're going parallel, so parallel velocity and acceleration, that is a factor of gamma cubed. And if they're perpendicular to each other, it's only gamma squared. So that's the difference in the accelerations in those two situations. But that's about acceleration. Okay, any questions here? This is also part of your homework, so. No, was it a part of your homework? Probably not. At least sometimes I give it as a part of homework. Okay, no, it's not part of your homework because your homework is to do with electric and magnetic fields. Okay. Good. Okay, so we have acceleration in this way. Proper acceleration has been defined. Now we need to define force or for force. Or for force, or you can say Newton's law in a sense will be equal to F alpha will be equal to the time derivative d by s of p alpha. I just have to make sure that it is the correct dimensions. So ds is distance, so we want to multiply by c, right? Yeah, so this is c. So immediately I can think of this as c dt over ds. So this is gamma times d by dt of p alpha. Right, that's my right hand side. Remember, your Newton's law is F equal to ma, right? So this is your F equal to mass times acceleration. So I'm mostly interested in the kinetic part or the inertial piece in there. What is that equal to? So this is time derivative of the momentum. So that's P alpha in here. So this is equal to gamma times 1 over c, change in energy over time and change in momentum over time. So maybe we should write this not in this manner. That's Newton's law, right? But here P is Newtonian. Right. Now we will have a very similar relation here, but now we want to recognize what is dE by dt. Okay, so let's calculate what first let's begin by saying, so this is kind of a definition now. The force will be defined as, remember that when you're doing Newtonian physics, force is an external input, right? The rate of change of momentum is equal to force. Force has to be again given to you in the sense that, for example, gravitational force is gm1 and 2 over r squared is an additional quantity that has to be given, like mg or force of friction. All those are inputs, right? That is a postulate if you want for each of the forces that you identify. But once you have a force, you know what it is. So that's dP by dt. So in a sense, this is again a definition or a postulate. Okay? So this is in Newtonian physics. What has changed? First, identify what the force is. If you know what the force is, write that as rate of change of momentum. The only difference is that P is now relativistic momentum, not the old Newtonian momentum. So this remains the same. This equation remains the same in both relativity and in Newtonian physics, except for the fact that P has changed. And you have to make sure that force is a relativistic concept. Electric field and magnetic force, Lorentz force, will remain the same in relativity. What about dE by dt? In Newtonian physics, what is the rate of change of, let's say, kinetic energy? Yes. No, not work. Right? Work is what is the rate of change of energy with time? Power, right? And power in terms of, let's say, or what is the expression for power?
Force times velocity.
Force times velocity, right? If it's a conservative force, only if it's a conservative force, it is force times velocity, and that will remain the same. These two equations will remain the same. So starting from here, this is equated to the force, and dE by dt, you can show that that's force times velocity. Okay, so these equations will be your Newtonian, or let's say, a relativistic equations of motion. Technically, this is sufficient, but it will turn out that for everything to go together, relativistic equations of motion. With the idea, remember that P is mv gamma, not mv. Energy is mc gamma, not the usual kinetic energy. With that in mind, all this goes through. So most of the classical mechanics, we have the same, except for the idea of momentum and energy. Okay. So let me do examples so that it's really clear what happens. Just as an application, I will do two examples here, and the more complicated examples of okay. Question. Question. Okay, yeah, okay. Okay, example. Example is a charge in a magnetic field. So a charge in B. If you're at rest in a frame, then what is the force on in a magnetic field? QV cross B. Right, so it is 0, right? So the force is equal to QV cross B. Notice this is not being changed. Right? Lorentz force is going to be a relativistic concept. We are not going to change that. Okay? That's not obvious at all, but it just turns out that it works out well. It is written in terms of magnetic field and in terms of velocity. So one would wonder, how does it go through? We will later come and show that it is a Lorentz covariant object. It can be written as a force, but that will have to wait until we show that. So for now, we are just saying that the force is QV cross B. It's not really clear that it should be a part of a force at all. So it should transform like a 4 vector. It is not obvious at all. It will turn out that it is a tensor and a velocity 4 vector that multiplied together gives you this. Let's wait for that.
That's for the magnetic force.
That's for the both magnetic and electric Lorentz force, which is having an electric field and the magnetic field. It's not obvious that it should be a Lorentz invariant concept. But it turns out that for Lorentz covariant, it transforms, it has meaningful, it transforms in the correct way. But we'll show that later, maybe 2 weeks down the line. For the time being, I'm just telling you that there exists a force. Let's say this is a force. And let's see what happens if this force exerts, if we do the kinematics of this force. Is that clear what I'm doing?
What charge is B here?
Charge is Q, charge in a B,
Oh, in a B.
charge Q in a B, sorry. Charge is not, sorry. Okay. So that's your force, and remember our new equations of motion are dP by dt is equal to force and dE by dt, the energy, is equal to force dotted with velocity. That's our equations of motion. So the right side is given to us. This is Q V cross B. What is the right side of energy? This is Q V cross B and dotted with velocity. What is that equal to?
0.
That's 0, right? V cross B, that's equal to 0. Right? So the energy does not change. Right? Which is not new, even in classical physics, kinetic energy does not change. Right? When you're going in a circle, the energy of the particle remains the same. Kinetic energy of the particle remains the same. Magnetic force does not do any work on the system. So this is equal to 0 there also. What does this mean more specifically? Let's write this again. P is M V gamma, right? Over dt. That's momentum. That's equal to Q V cross B. Sorry, Q V cross B. And here the condition is d by dt of mc gamma, right? Energy was mc square gamma over c, so that's equal to 0. Mass remains the same. Speed of light remains the same. What this means is that gamma is equal to a constant with time. Gamma is equal to a constant, which means that the velocity remains the same, right? So this means that the speed v dot v, right, the magnitude of velocity remains the same. Is that clear? It can change direction, but the magnitude of the velocity remains the same, or beta square is equal to the same. Question? Yeah. See.
Yeah, here we write P alpha is equal to mu alpha. And in terms of U alpha, we can write MC gamma, MB gamma, like that. Yeah, that one.
Mhm.
In the same way, when you are taking the F alpha, can't we take it as A alpha and take that A alpha, the ones we found earlier?
Yes, we can. So you're saying this whole thing will
Yeah.
go through here. Yes, that's correct. That's perfectly fine. That is okay.
Yeah.
But okay. Correct, completely correct. But this becomes convenient. Remember, Newtonian physics has this connection, right? So when you write it in this form, you're saying that all the equations remain the same. If you explicitly do it, you're actually doing it. For the simple scenario where QV cross B is happening, so I told about A parallel to acceleration and or velocity parallel to acceleration, velocity perpendicular. We're actually doing this. For all practical purposes, you will have to do this. Right? But this makes connection with what we already know. So it is easier to remember in the long run. Right, this is there every time you have to derive it from here to there in your head, you have to derive it. This is already there, it's already inbuilt in us, so it's very convenient to keep this. But you're correct that if you want to connect this, then this is what it is. That is the what it is. Absolutely no difference. But we are going to do that every time. Instead of remembering this, we'll do that every time. So for the magnetic case, this is what has happened. So we are actually doing it, right? Kind of. Okay.
Can you explain the last two?
This is this equation here. And that's this equation here. Right? Momentum mv gamma, energy mc, and c square. Is that the confusion? Right? mc square gamma, that's equal to 0. Right? In our situation, this is equal to 0. But the moment you get this, that means gamma is equal to constant. Right? Because mass is constant, comes out c square is constant. And the moment gamma is a constant, gamma is 1 over 1 minus beta square. That means velocity is a constant. Right? So whatever happens in a magnetic field, you cannot change its speed, not the velocity. Speed cannot change.
So there are no like divergence, curl of divergence is 0, right? That's the
Curl, yes, this is 0. That's why so this relation is what I wrote here.
so it's gonna be 0 because that
This is not curl, right?
Cross.
Cross product. Is that what you meant?
so how does that become 0 like?
Because cross product, right? Cross product will be perpendicular to both.
Yeah.
And then you take a dot product with that. So that's it. This is B. Right? That's your B. Cross product is this way, right?
Yeah.
So that's B cross B. Perpendicular to both. Now take a dot product with V. Right? So always since it's perpendicular, you go back to 0. Unless, yeah. I think this always comes out. The case, I think. Yeah. Okay. With me? So main thing is gamma is a constant. Right? If gamma is a constant in time, this can come out here also. Only in this configuration. In a magnetic field, gamma remains constant, it can come out. So I write this, and now this step written again. dV by dt is equal to V crossed with, that is a Q times B M times gamma, which I write it as a vector omega, where omega is Q times the magnetic field over M times gamma. That's the definition of cyclotron frequency. That is Abdullah, right? He was the one who pointed it out, right? Except that there is gamma in the denominator.
It's not cyclotron frequency.
This is exactly the cyclotron frequency, except now it's a relativistic cyclotron frequency. And it contracts. Right, the gamma is in the denominator, so it is it's smaller than the cyclotron frequency in the if you had a rest frame. If you have such an equation, you don't, I mean, if you remember, if you were to do this for classical mechanics or Newtonian physics, gamma is not there, and this is the same equation you will write. The moment you get this equation, what's the solution for this? It is circular motion. In fact, what it means is that if there is a precession, right? This is velocity is precessing around the magnetic field. That's what you can look at it as this is a precession equation, that the spin satisfies the same equation. But once you have this is circular motion. That's the same Newtonian physics, and I'm not going to do that. Okay, but you should all know how you can prove that it is circular motion from here. Start with some initial condition, do the write the x component, write the y component, and do that. Show that this is circular motion. Okay. So the only thing that changes in relativistic physics in a magnetic field is that the cyclotron frequency has shrunk a little. It has got smaller, the gamma is larger. So that's the only thing that happens in that. Is that clear? Arguments that went through it? That's your equations of motion. Because this is a dot product here that goes to 0, gamma is a constant, kinetic energy remains the same because velocity is the same. And use that in the other equation, and you get this. This implies circular motion even in the earlier. This is the same Newtonian equation you have. So that's a quiz problem, right? Just use that as a quiz. Show that as a quiz. That means do it for your own purpose. Satisfy yourself. That's it. That implies circular motion. Okay, so any questions? Okay, comments?
So which means from the previous class quiz, you gave that to find the trajectory of a charge
Of a charge
Yeah.
in a magnetic field, the answer is circular.
circular but with the shrunk frequency.
With the like if you're in a norm, if you're on the rest frame, it goes like this. And if you're in relativistically speaking, if you're in the same particle is moving and you see it from the lab, this will go slower, significantly slow. Or the frequency, right? Time period is actually dilated. Yeah, so it is slow, correct. Less number of times, right? That's all. So that's the only difference, nothing else changes. So actually, yeah, go ahead.
The circular motion, do we have to prove from the equation?
Yes. If I give you this equation, why should it be circular? Who says? Who tells you that? Right. So you can do the standard different. There are three equations here, right? dvx, dvy, dvz, and choose the magnetic field in a certain direction if you want, but don't choose it if you don't want. And write those three. Those are three differential equations, but they're coupled. X will be dependent on y, y will be dependent on z, so on. And put them all together, solve for it. You can solve for velocity, then integrate it again, you get a position, and you have to turn out that it's an equation of the circle. So it's a little bit of work, you need a little cap, but it's, let me not do it here. That's why it's a quiz. If you're not able to do it, ask me. It's I ask these questions here and there. Like in an exam, it's a favorite question because I can. That's the background, right? Makes sense. And make it simple if you want. Use the magnetic field in the z direction. Velocity is initially in the x direction, something like that. So that's a simplification. So, and it's even better. Notice that this is a vector. Rate of change of vector is dependent on the vector itself. Like it's like the torque. If you think of a top, torque, like a top in a magnetic field, that has a very similar equation. There it is the angular momentum. The rate of change of angular momentum depends on the angular momentum crossed there with the gravity. So there also, if you notice, the L is actually going in a circle. The same equations comes into picture. If you have a spin, which is basically the angular momentum, spin in the magnetic field, that will precess, it's called precession. The same idea here, circular motion. The same equations basically, but the interpretations are different. Okay. So, any more comments, questions? Okay, so we go to electric field, right? So charge and electric field. And now we have the possibility that charge could be at rest, it could be moving in a direction, it could be in the same direction, it could be in a different direction. So let's say the force is equal to Q times E. And the electric field, let's say, is equal to E times the J hat direction or Y hat. Y hat direction. And now I need to give the initial velocity. So V initial at time t equal to 0. So V is 0, right? That's initial velocity. That's equal to 0. It starts from rest. Once the velocity is given, I can do the integration again, and I should also tell you where does it begin from, right? So let's say position as a function of that. Or at time t equal to 0, I say is equal to 0 in the x direction plus a constant in the y hat direction plus 0 in the z hat direction. Notice I have not chosen this to be 0. I could have, right? But it's just convenient to have that at y naught that we will see that as we proceed. That's the reason why I choose such a
Why
non.
did you choose put the vector sign for the velocity?
Because that is, you mean this way? Is this better?
Like you meant three of them are 0.
Yeah, all three of them are 0. That's what I. So it's truly at rest that in that particular lab frame that I'm working on. That's what. So that's our configuration and electric field. Is in the white dash. Okay, so again, equations of motion. So that's our equations. So we have m d by dt of momentum gamma is equal to force, right? Force is Q times E times the y hat direction. And our energy is d by dt of mc squared gamma is equal to y hat dotted with velocity, right? So what is that equal to? So in general, V is not like this, correct? It is having any direction. So it is Q E V Y. Like the force times the velocity, but this is only the initial velocity. So that's what it is equal to.
Yes. One space or before that.
Yes, that's what one has to. So this is the spatial force equation. This is the time force equation if you want. Like we don't worry about it so much in the Newtonian case, but that also energy just is a separate concept that it's related to the force, but here it's kind of inbuilt in. Yeah. Okay. Let's explicitly get this. So that is a D, so we can do this better, right? That is mvx times gamma is equal to 0. D by dt of mvy times gamma is equal to Q times E. And d by dt of mvz times gamma is equal to 0. That's clear? Think so. Second one is this one.
No, the second
This one, this is all independent, so this is this equation.
Okay.
This is the energy is equal to F dotted with V. F dotted with V is QEV, right? So maybe do this in steps. So this is QE dotted with velocity V.
Okay.
But electric field is only in the Y component, so it is QEVY. Okay. So that's. Okay. Well, oh. Okay, what else can I do?
Now we can find y, Vy. And use it for the energy.
Yeah, but for that, this has this X and Y in it, right? So that's what I'm worried. Remember, gamma is equal to 1/1 minus Vx square plus Vy square plus Vz square over C square, right? So first I have to convey that Vx and Vz does not change, right? So I go here, right? So this implies that Vx gamma is a constant. Right. That constant I can pick from at time t equal to 0. That constant is the same at any time. So that's equal. So that's called maybe this is a constant. And that's equal to Vx0. So that is Vx at time t equal to 0 divided by 1 minus, or gamma is 1 at that time, right? Yeah, maybe write it like this. So this is equal to Vx and gamma at time t equal to 0. Gamma is 1, x is equal to 0, so that's equal to 0. Right. Because Vx at time t equal to 0 is 0. Right, that's an initial condition. So this implies that at every time Vx is 0. Gamma is not going to be 0. So I have shown that Vx remains 0 at every time, only in this configuration. Do the same thing here. This implies that Vz is equal to 0 at every time. So together you can show that means that gamma is only Vy, right? 1 minus beta y square. Vx and Vz is 0, so that's gamma is purely is contributing, getting contributions from the y. Okay. So I think in that case, this okay. Yeah. Okay, so we have one condition here. So I mean, I can erase this. So I've used these two quantities. I have only these two things remaining at this point. And that's your force. Hopefully this is correct. Okay, so d gamma by dt. So this is equation 1. Okay. And that's equation 2. That's the only thing I'm interested in. So 1 implies that d gamma by dt is equal to QE over M. And then there is Vy over C squared, right? Vy, yeah, this is a Vy. Correct. So is that dimensionally correct? So that's acceleration. Acceleration, that's 1 over time. Acceleration velocity, so that's velocity square over time, yeah, so that's 1 over time, so that's dimensional. Let me define QE over M to be alpha. That's like an acceleration, so that this is alpha. Okay, so I'm going to write this as a constant alpha Vy over c square. That's the equation I have. The second equation in the same way is equal to this down here. So it is d by dt over Vy times gamma is equal to alpha. Okay, so that's your two equations. I've just simple manipulation I've done with some variables in there. This is a constant. I immediately, so 2 implies integrate them. So I have Vy times gamma is equal to alpha t plus a constant. At t equal to 0, Vy is equal to 0. That's equal to alpha times t, since t equal to 0 implies Vy is equal to 0. Right? So we have a relation like this. Okay. Rewrite this equation again, Vy square over 1 minus Vy square over c square is equal to alpha square t square. Question? I just squared this. If gamma square is 1 minus beta square, which is Vy square. No, I just squared this. Do this slowly. Confusion, okay, Vy square gamma square is equal to alpha square t square. True statement. But gamma square is 1 minus beta square, so it's Vy square over c square is equal to alpha square t square. You would like to integrate, you're correct, but I first want to get the expression for velocity in a few minutes. You guys have to be somewhere. Can I take 5-10 minutes extra?
That's fine.
Okay.
Yeah.
Yeah. Okay, so put this together. So this is Vy square is equal to alpha square t square, and multiply this again. So it was minus alpha square over c square t square, and that is a Vy square. Get this onto the left side. I have velocity y square is equal to alpha square t square divided by 1 plus alpha square over c square times t square. Divide it out by both sides by c and rewrite this. So what I want to write this as beta square, let's say. Probably beta square. Let's stay as this. Oh, I shouldn't have erased this. And take a square root, and what you get is dy by dt is equal to alpha times t divided by 1 plus alpha square over c square times t square square root. Is that it? Take a square root on both sides. So that becomes alpha t.
dy by dt.
Because velocity Vy is derivative with
Okay.
like Vy is equal to dy by dt. Like same idea as what we do in classical mechanics, uniform acceleration, except there is this gamma floating around. It's a little mixed up in that sense. If I want position, integrate this, right? So, and there is a constant of integration. So it is some constant. And integrate from dt. So that's alpha t over 1 plus alpha squared c squared t squared. Substitute 1 plus alpha squared over c squared t squared is equal to, let's say, s. So alpha squared c squared 2 times t dt is equal to ds. So dt, yeah, tdt, right? Tdt. So tdt is equal to ds over 2 alpha square over c square. So put that in here. So that's equal to, this is ds times 2 alpha square over c square. There's already an alpha there. And that is a square root. No, that's, yeah, square root of s. Right. Put this all together. Alpha cancels out. And that is a c square over alpha. And integral of s raised to minus half, right? Plus 1 divided by minus half plus 1. The 2 cancels out with this 2. So that's square root of s. So y minus the constant is equal to c square over alpha. Substitute back your s. It is 1 plus alpha square over c square times t square. Okay. Put this in. Maybe. Yeah, let's do one more thing. At t equal to 0, like we want to fix this constant, right? At t equal to 0, I know that y is my position, so y naught minus this constant is equal to t equal to 0, it is c square over alpha. So constant is equal to y naught minus c square over alpha. I have the choice to pick wherever I want my constant is. Let me put my initial position to be this itself. That's just a choice to make this simple, just to get this constant 0. It's not necessary. Let y naught be equal to c square over alpha. That implies that the constant is equal to 0. I get rid of my constant. That's just a special choice just for simplicity in a sense. So this is 0 now. So I have y squared is equal to c squared over alpha squared and 1 plus alpha squared over c squared t squared. So it's equal to c squared over alpha squared plus c squared cancels out one of the alpha squared also cancels out, except there is a c squared t squared remaining. So the equation of, or the trajectory, or as a function of time is c squared over alpha square. That equation should be very familiar. We have come across this before. That's the equation of a hyperbola. Right, y squared c squared is equal to a constant, and if you were to plot this, so if you allow me to erase all this. So if you were to plot this. This equation is. Since at time t equal to 0, y is a constant, we said that's c square or alpha. That's your hyperbola. Yeah. So this is the equation for this is y, that's c times t. That's the equation for c square alpha square plus c square t square square root. We know that this is in Newtonian physics parabola. How does that come about? Let's consider the situation where the time is very small compared to this. So c times t, c square t square over is very much small compared to, oh, that has to be large, right? So this has to be small. So c square t square, no. Oh. I want to expand it, I suppose. Yeah. I think so. C square t square is very much small compared to c square over alpha the whole square. So that means this is small compared to that. So this is equal to y is equal to c square over alpha, and then square root of 1 plus c square t square over c raised to 4 times alpha square. Since this is small, I can expand it. C square for alpha 1 plus 1 by 2, that is your 1 by 2 coming up, times t square over alpha square over c square. And there are higher orders possible. This is equal to c square over alpha plus half. Neatly, the c square goes away. Newtonian physics has no information about speed of light. Alpha square plus 1. And the choice of that constant being 0 was made by y naught is equal to c square over alpha. So that's nothing but y minus y naught is equal to half alpha t square equals Newtonian parabola. If you had plot this here, this will come out as this. That goes out as a parabola. That's y minus y naught is equal to half alpha t square, with the understanding that this is y naught, which is basically c square over alpha. Yeah, that's a special choice. You will pretty much redo this for the case when it is perpendicular velocity. So even though I went in a hurry, hopefully it will be clear. Thank you. Sorry about the extra time. Did you have to be somewhere?
No,